So, welcome students. So let's wait for a few more minutes, then we'll start. Okay, meanwhile all joins, so we can continue what we have done. So in our previous class, we talked about the gel electrophoresis and how DNA is going to migrate in the under the electric field. So in that we talked about the agros and so on. And now the practical part, the main thing, how to perform the experiment. That was remaining. So before continuing to how to perform the experiment, what are the different requirements? I would like to ask you any query regarding what we have discussed here. Do you have any query? No response? Am I audible?
No doubt, sir.
Okay, so no doubts. That's fine. Okay, so then we have to wait for a few minutes. Meanwhile, all join. Then we'll start. Okay, so now number is well. Okay, we can continue. So now thing is about the performing the experiment, and performing the experiment means you need thing, and as we talked about the component. So component of the electrophoresis are on the basis of one as the electric field. You need a power supply for that. Second component is you need a gel. It's gel electrophoresis, that is matrix. So in case of our case, agarose gel electrophoresis. So agarose is that one. And electrophoretic unit you need. So where the electrophoresis you are going to do, you will perform. And gel casting tray is going to be required where you are going to cast your gel. So that's another requirement. Then you also need buffers. So as previously we were talking about that buffers you need for first for the purpose of the pH and second for the purpose of uh, conduction, because your you need electrolytes to conduct the electricity. So buffer also have the electrolytes in them, so they are going to help in the conduction of the electricity. So these are the things, these are the requirement of our electrophoresis that we need. So you can say simply, if we talk about aim to perform the aerogel electrophoresis, metal you are going to need centrifuge tubes you need, so in which you are going to prepare your sample. Micropipette you need, so micropipette for the transferring the or handling the sample. Tips and the micropipettes both are required. Power supply you need. Gel tray for preparing your gel casting tray also you can call it. Well comb, so in the gel where you have to place your sample, so for that you need a well comb also. Tape you need, so tape you require for the sealing, because when you want to conduct the electricity, your gel tray must be open from the two sides. If it is going to be sealed from any of the from all the four sides, like it is going to be as a spare block, so then it is you can't conduct the electricity. If the electricity is not transferring or not conducting, then particle will not move. So for that you need to seal. So I will show you how to cast that. I will show you the video also of that. So that will give you in the detail how to prepare the gel and gel casting gel and how to cast or how to run the electrophoresis. Transilluminator you need. So transilluminator is required for the observing the DNA. So you can see the DNA with the transilluminator. So transilluminator is going to have a UV radiation in it, and also gel documentation device. Sometimes we also call gel doc. So gel documentation simply means you want to capture the image. So it's going to have a filter also. So using the filter and camera, you can capture the image of your gel. Then DNA sample you need, sterile water you need. So these are the things that you need. So now come over the chemicals. What the chemicals you need to perform such experiment? You need buffer. So buffer is going to be TAE or TBE, as we already discussed about two different buffers you can use. And okay, so I think we were at the buffer in our last class when we were talking about. So I can open that one. Just hold for a moment. Okay, so we were here at in our last class that talking about the buffers. So buffers are going to be the buffering capacity is there. So how they can resist, how what type of the things they can provide you. So two type of buffer we are using in this case. One is the TAE or the TBE. So both buffer have different uses. So if you need a high buffering capacity, we are going to use TBE. But the main problem with the TBE is that it is a bit expensive. So if you want to need a cheaper buffer, For that, you need to go for the TAE, but the buffer capacity of TAE is it's lesser as compared to the TBE. But for your frequent experiment where you don't bother about the buffer capacity, you can use the TAE also. So the main difference you can see in case of TAE, tris and acetate is there, where in case of the borate is there. So acetic acid is a bit cheaper compared to the boric acid. So rest of the components are common. So the cost mainly that cost difference that we are seeing in these two, that is because of the borate, not because of the tris and ETT. Okay, so these are the about the buffers so that you need and that you prepared. And another one, that ethylene bromide I mentioned. Ethylene bromide is going to be intercalating agent. It intercalates between the grooves, that is the minor grooves. So when it intercalates in the DNA in their grooves, so then it fluoresces. Okay, so this is the role of your ethylene bromide, and it fluoresces in the UV light and emit in the visible range, that is the orange. So then how much you required? So what amount you need, so that how much it can detect? It can detect a very small amount, 20 nanogram DNA it can see easily. And how much concentration of the buffer you need to make, that I'll show when I talk about the buffer, what you need to make. And the voltage that I mentioned, continuous voltage supply you need. So these are the requirement in the theory part that we're talking about. Now we can move to the material and the procedure, how you're going to perform. The material I already talked to you. I told you how much that you need. So now what are the buffer composition you are going to do, how buffer you are going to make. So for that we need to move to our Word file where we have described the different buffers. We'll come back here also for certain some requirements. Okay, so now come to the thing. So the TAE buffer, 1x TAE buffer you need. So the composition of TAE, just a moment, is composition of TAE is there. Just a moment, I'm bringing you the composition of TAE and TBE. So this is the composition of how to prepare the TPE buffer. So this is the one. So you need to add 108 gram of tris, 55 gram of boric acid. So this is for TPE, 55 gram of boric acid, and uh, this EDTA 0.5 molar EDTA, that is a 7.5 gram. That these things you need to add to prepare your TBE. And as I was saying that when to use TBE. So the main thing, so TBE is having high buffering capacity. So we use TBE when you want to run or you want to need a higher resolution. So that's the higher resolution. So you want to separate a smaller fragment. Okay, so that is the conditions. If your requirement is that type, then you are going to use TB. So simply as I'm saying, fragment superstar smaller than a 2 kb, then you should go for the TBE. Okay, so then after the next type of buffer is the TAE. So TAE and TB, as I mentioned, that they are differing in the acetic acid of the borate. So the preparation wise, whatever the composition of tris and EDTA is going to remain common. There is no, you're not going to change those things. But the main thing that you are changing is the borate is there. So acetic acid. So here you are preparing the acid. But one more difference is there. If you can see, the TAE buffer being made 10x. Wherever TAE buffer you can make up to the 50x. Okay, so that's why if you check the amount of the tris that you need to, here is the 242, and in the first case you are getting only 108 gram. Okay, so this is all the requirement that you are having. Okay, so then coming to the saying when you should use. So here, if you do not bother resolution and you don't want to run very long, your run time is very short. So in that case, you can go for with the TAE also. So these are the things when you can go for the when you can use TAE buffer. Okay, TAE buffer better for the cloning type of experiment that you want to go. So you can use. So the composition wise, simply if you want to write what you are going to add, so simple recipe we can write here as a tris. We need to add simply you need 108 gram. Then you need EDTA. EDTA you need 7.5 gram, and you also need boric acid in case of so 55 gram of boric acid. Okay, so this is the recipe for TBE, and this recipe is not for just, it is for 10x. So this x I have already told you, this is a multiple. So this okay, so this is of 10x TB, but when you are going to work for when you want to use it in your real experiment, in that case you need to go with the 1x. So you have to dilute it. So this is your stock solution. So this is the stock solution of TB. Similarly, the stock solution of TAE. So stock solution of TAE is going to be 50x. So in case of the TAE, what you need, how to prepare it. So same three components are here also. So tris, you need to add 242. So weigh the tris 242 gram. And next thing is going to be your EDTA. So EDTA you need here similarly 7.5 gram. So it is 18.7 0.61 gram. So reduced to fire. And next is going to acetic acid. So acetic acid is a liquid. So you need to add it into ml, not into the grams. So acetic acid is going to be in liquid form. So this volume you have to add the 57.1 ml. Okay, so this is a recipe, but this recipe is for the 50x. Okay, so this is the recipe of 50x TAE. While working, you need to dilute it again for the 1x. So this recipe is for the volume of a liter. So 1 liter if you want to make, then you need to add to that 242 gram of tris, 18.61 gram of EDTA, and 57.1 ml of acetic acid. In case of TB, you need to add tris 108, EDTA 7.5, boric acid you need to add 55 gram. So this is the recipe for your tris buffer, TAE buffer and TB buffer. So requirement when to use, ideal conditions. Ideal condition for TB is a higher resolution, smaller fragment, longer run. Okay, because it have high buffering capacity, it can sustain for long. And for the TAE, if the run is not larger, fragments are very large in size. So large size fragment you can separate in shorter time. So size should be more than 3 kb, and buffering capacity here is low, so you need to work accordingly for a shorter duration. And the preparation thing is that stock you can prepare, but when you prepare the 1x, you can use it fresh. You make it fresh when you're preparing the buffer. And in case of TAE, you can not reuse it, but TB you can reuse it because the TB is going to have a large buffering capacity. Next requirement is going to be agarose. How much agarose powder you need? So agarose powder required on the basis of how much volume of gel you need to make, and what percentage of agarose you want to make. So we mentioned that we can make up to 0.7 to 3% of the agarose. So like you want to make 1%, 0.75%, 1.5%, how you need to calculate. So if you want to make 1% gel and the 100 ml gel you want to make, then you need 1 gram of agarose powder. So agarose is going to be in a powder form. I will show you on also some components today in the lab. So what different components of the electrophoresis are and how the agarose look like, how to cast the gel. Wait a moment. Okay, so this is the thing, and actually the bromophenol dye. So this bromophenol dye you need as a tracker dye to track the migration of DNA. And ethylene bromide you need. Ethylene bromide is going to be 2 mg per ml of the solution you prepare. And next is the DNA letter. It's also a company made. You are going to get from the directly from the company. So these are your requirement principle. Casting gel, everything we have talked about. So how to you need. So this is a gel casting tray. How it is going to look like, you can see it here. And with this blue color, you are able to see these are the foams. So in foams, it is just like your form that the teeth your foams are going to have. Here also teeth are there, but teeth are a bit broader, and their width is going to be more, thickness is going to be less. So this is the design of your form you can easily see here. Okay, so this is a power supply you can see, and this is gel unit. So and in it you have placed your gel, and in your gel tray is there. This blue color that you can see, they are the well. And this is your gel documentation device, so also called the gel illuminator or gel documentation. Inside it is going to give you UV radiation. Under the UV, you are going to see the bands, and it is going to have a camera also, which help you in taking image. Okay, so the methodology, for the methodology I will discuss in detail later. Before that, I am showing you some video. So that video will tell you how to really perform a gel electrophoresis experiment. Hold a moment.
Because of course some of the migrate.
Okay, so I'm sharing a video. So watch the video, and after the video, we will join back. Are you able to see the video?
Yes, sir.
Okay, so I'm playing.
Yes, sir.
I have here this lovely little gel mold, and I'm going to seal the ends of this mold with just regular old masking tape. Mind you, it has been wiped down with ethanol. So we're going to push down just like a Christmas present. Push the ends down. Push to make sure that when we pour our agarose in here, that it doesn't leak. And we do the same thing to the other end. So that should do it. Now, a lot of people put their comb in after they pour their gel, but frankly, I've never seen any difference. I've never seen any bubbling around the teeth of this comb. So I just usually put the comb in immediately. Now, I'm going to make the regular agarose gel. So I'm just going to move this out of the way for a minute. And I have here in this little whey boat about 0.32 grams of regular agarose. You can't really see it. It's very pale, and there's not a lot of it because I'm making a 0.8% regular agarose. So I have here a 250 milliliter flask. Because of course some of the agarose in the microwave, let it come to a boil. Now we're going to let it cool down. And we're going to put a magnetic stir bar that's been sterilized in into this flask, and then we're going to turn the stir plate onto its lowest, excuse me, lowest setting. And it takes 2 or 3 minutes for that to cool down. And while it's cooling down, we're going to set the pipette. We're going to put in 64 microliters of loading dye. So nice and easy, pretty wet. It's cool enough, still very warm to the touch. You don't want it to solidify in the flask. And there's the 64 microliters.
Sir, the video is paused at 9.
Dye that will help us visualize the bands of DNA. Now that looks evenly dispersed, that dye. So we're going to take a couple of large magnetic stir bars to anchor the small one that's inside. And now we're going to slowly pour this agarose gel. Oh, and that'll take 20 or 30 minutes to set. So this 0.8% regular agarose gel took 20 or 30 minutes to set, harden. And I just put it down into the gel rig. The rig has the same buffer that we made the gel with. 1 times Tbe buffer. It's been sitting in there for a couple of minutes because we want the buffer to be able to get around the teeth of the comb so we can easily extract the comb. And after we do, we're going to put in the DNA that we digested overnight using restriction enzymes. And then we're going to run it. Make sure that you're anchoring, holding down. We're going to take this comb out. This is our DNA standard, or ladder. And I'm putting in 10 microliters of ladder. And here we go, there's the well. Nice and slowed into the well and down into the second stop. And release the micropipette plunger. And now we're going to get a fresh tip for every sample. This DNA is digested with only 1 enzyme, so we know where this enzyme cleaves DNA. This enzyme is PS-T1. And we're going to load that. Second well. Slowly. There we go. Excellent. This third vial is digested with PST1 and a second restriction endonuclease. So we're going to have DNA of different sizes. This has been digested with 3 restriction enzymes. So we'll have multiple bands appear on this well. Down into the well. And voila. We're ready to put the leads on. Black to black and red to red. This end is the negative end. This is the red. It's the positive end. I want to make sure that we do the same in the front. Connect those leads. I'm going to run this gel at about between 100 and 130 volts. that's when we're going to turn it off. Then we're going to look at our bands on the light bulbs. So we have run this 0.8% agarose gel at 130 volts for 45 minutes. And we turned it off, and we stained this with a small amount of dye for 20 minutes. And then we de-stained it, rinsed it in ultra-pure water for another 20 minutes. And you can see now we're going to look on the light box. Slide this right off onto the light box so that we can look at bands. And you can see here fragments have separated sufficiently, it's time to visualize them. This is done with the aid of chemicals which were added to the molten gel before it was poured. Cybergreen dye can be used, but the best and therefore most commonly used chemical is lithium bromide. These chemicals stick to the nucleic acids and fluoresce under ultraviolet light. Cybergreen is safer but less sensitive than lithium bromide, which is a strong mutagen. In order to have a permanent record of the fragment separation of the gel, you need to take a photograph. This is done by placing the gel on a UV illuminator inside a box which also contains a camera. The illuminator is switched on and the gel image is displayed on a computer screen. The image can then be saved as a digital file or printed out. When heating an agarose solution, it's abnormal that a loose top is placed on the container. If the top is too tight, there can be dangerous pressure build-up within the container which can cause the container to break. When making an agarose gel, don't leave the gel solution unattended while it's heating in the microwave oven. A solution that's heated for too long will lose water, increasing the agarose concentration of the final gel, or even burning the gel mixture. Don't remove the kernel from a gel before the gel is fully set. That will cause the walls between the wells to be destroyed and the gel will be unusable. Take care not to damage the wells when loading your samples. A damaged well can allow the sample to leak out and may cause contamination of other wells. It can also cause nucleic acid fragments to migrate unevenly. Make sure you don't load air into the wells along with your sample. Air can cause samples to be lost from the well into the buffer solution and can also cause contamination of neighbouring wells. Another mistake that can be made when loading a gel is to load the sample too quickly. This will also cause the sample to flow out of the well. Once you've loaded your samples, take care not to move the gel. Even a small movement can cause sample loss and contamination. Agarose gels are used in molecular biology for the separation and purification of nucleic acid fragments. A dye is added so that the fragments can be visualized under ultraviolet light. The samples are loaded into the wells of the gel and separated by size using an electric current. The size range of fragments that can be separated using agarose is between about 0.2 kilobases and 20 kilobases. Agarose gels can be made with varying concentrations of agarose, between 0.6% and 3%, depending on the size of the fragments you wish to
I just checked that some of you messaged that video is not visible to you.
Yes, sir.
Sorry, might be that happened because of some network issue. Okay, so now we are concluding this session, and I will continue, and I will explain you. I will show you that video again, and I will also explain you how really. I will also show you in the lab what are different components and how to cast the gel, and how to perform your experiment. Okay, so we'll join back after 5 minutes. So till then, stay safe, stay happy. Good day.
Thank you, sir.